Good morning, everybody, and thank you to AIVC and TightVent for inviting us here today to talk about pulse. Sorry about my voice, it's a little bit croaky this morning. Now, the story of pulse is not new. It goes back over 20 years, and many of you may have known the late David Etheridge, who started this back in the 90s. And then this work was then taken over by Dr. Ed Cooper. And indeed, my own journey started in 2014. My name's Chris Wood, and I'm an Associate Professor of the University of Nottingham. And I'm joined today by Luke Smith, who's also been on this journey with myself since 2014. He's the Managing Director of Build Test Solutions, who now manufacture and commercialise pulse. I'm also joined today with Xiaofang Zhang. Many of you may know as Ken. Ken has been a researcher involved in pulse since around about 2013. And he's here, of course, for those great technical questions at the end as well. So, what is pulse? I think we'll start off by just reflecting on the steady pressurization method, otherwise known as the blower door technique. And many of you will be familiar with this relationship of leakage and pressure. Indeed, the power law relating pressure to some flow coefficient and multiplied by the pressure up to the raised to the power of the exponent there. So with the blower door, we're at higher pressures, typically taking measurements between 10, 60 or 70 pascals, pressurization and depressurization to get beyond sort of the vagaries of wind and buoyancy. And indeed, the steady pressurization test is a robust test. There's no doubt about that. In science, we actually like a steady technique, and this is one of those. But pulse is a low pressure technique measuring at 4 pascals. So we're right down there at the bottom there. Now, that, of course, is within the realms of the pressure differences that we would expect on buildings. So what is our motivation? So the primary motivation, going back to the work on the thoughts of David Etheridge back in sort of the 1990s, was a pursuit to develop, sorry, I've got this in front of my screen, was a pursuit to develop a method for testing the air leakage of large buildings. So if we think about that relationship between leakage and pressure difference, and as we go to increasingly large buildings, increasingly leaky buildings, then we're going to require much larger airflow. So in its initial form, the idea was to look for a way of being able to test those large buildings without the need for such large airflows. And we also wanted to do it much more quickly as well. So as I say, we're thinking about those large buildings with the large fans, trying to do something more quickly. The way to do this would be to try and find something, a method, a technique at low pressures, while still accounting for those effects of wind and buoyancy. So the underlying principle is what's known as the temporal inertial model. And if we start by thinking of a pulse in a piston, so in this simplified diagram here, we've got a building with volume V, with an internal pressure and an external pressure there noted on the diagram. We've got a piston that pushes a pulse of air into that space, and then we can sort of intuitively think about what that might look like. So between the points 1 and 2 there on the right hand side, we're recording what would be the background pressure. The pressure that would then rise within the space, within that building, up to a point, and depending upon where that piston is within its travel, if it's towards the end or coming towards the end, we could expect a point where the air and the gaps and the cracks of those buildings overcome the inertial forces and it start to flow. Now, we would then see some sort of fall, maybe a decay, but also perhaps a force flow if that piston is still traveling. And there you would get this kind of representation that we see there. And this is a typical pulse curve, and I'll talk a little bit more about that in a couple of slides. So on to a little bit of the maths. Suffice to say that there is some maths behind all of this, and this is the temporal inertial model that David Etheridge set about back in the sort of the late 90s, early 2000s. And we can see that we have a flow which is flowing from the building, little QT there, which can be related to this flow from the pulse, and a change in density within the building. If we assume isotropic expansion there as a constant, then actually that the flow, small qt, is equal to the flow from the piston subtract then this part of the formula, which involves in the change of pressure. So if we're able to measure the pressure change within the building, and we're able to know something about the flow that's going into the space, we can work out the leakage from space. Now, this momentum equation, which looks at the change of pressure, has three components. Those first two components are related to steady flow, but the challenge has always been this third component, which involves the inertial term. Essentially, when you think about the change in velocity of the air going through those gaps and cracks, that the inertia is actually a problem, because that represents unsteady flow. The challenge, therefore, is to create a pulse, and at least a part of that pulse where that unsteady flow part tends towards zero. It may never reach zero, but it's certainly a minimum, and there we can calculate the flow. So this was the sort of initial piston. You can see there's a compressor there which drives a piston which pushes a pulse into the building. Now that's obviously quite a large piston, isn't it? So to get away from that large piston, it was to replace that with a nozzle. And this was the work of Dr. Ed Cooper back in 2006, where the mass flow rate could be related to the initial pressure within the vessel, and we know the volume of that vessel, of course. And by measuring the temperature and the pressure within that vessel, we could work out the mass flow rate. And assuming we have a uniform internal density within that vessel, as I say, we can calculate the mass flow rate. In sort of the development since then, we've got a more advanced process where we're constantly monitoring the change in temperature as well as that air is released for a more accurate measure of the mass flow rate. So our pulse shape, we read the background pressure before the valve opens, and then as that valve opens at around about 2 seconds, the pressure inside, so we're looking at the dark blue line here, by the way, the pressure inside the building starts to rise as the pressure in the tank falls. And then we hit this point, which is the quasi-steady period. The quasi-steady period lasts for probably around about 0.6 to 0.8 seconds. And at that point, the air is actually flowing through the building, but also still being released by the tank, the air receiver. So it is a forced flow. And at some point, the valve will close, the pressure in the building will decay, and we can read the background pressure again. Here is a test repeated 5 times, and you can see different background pressures, which may be caused by the vagueness of the wind. Point being, it is repetitive, and we can correct for those background pressures because the time in this, the duration, is so short. So early testing involved repetitive testing in lab chambers and real buildings, in sheltered and unsheltered environments, many different forms. This talk, there's a whole list here. I haven't got time to read them now because I'm running out of time, actually. CFD modeling of the pressure distribution within the air receiver. So that's ensuring that that uniform pressure within the tank, and that assumption holds true. CFD modeling and experimental validation of the pressure distribution in a building. So that's taking a large building. We took a 5-bedroom building in one case and did both CFD modeling and took measurements within that building to see that assumption held true as well. There's been around up to 20 to 30 papers, peer-reviewed conference papers, and 3 PhDs that have actually been undertaken with this work. So pulse progression over the past 20 years was from a piston being driven by weight, a piston being driven by a compressor, to the nozzle technique, to a more packaged full unit with the compressor and a plastic vessel, to a more of a roadie type case with built-in computer in there, which gives out the results. And that leads me in quite nicely to where we are now with Build Test Solutions and Luke and the current product. Luke, do you want to request control? There we go.
There we go. Brilliant. Fab. Thank you, Chris. Morning, everyone. My name's Luke Smith from Build Test Solutions. So we're a company set up based in the UK, set up in 2016, and we essentially have taken the license on this intellectual property that the university have developed in Pulse. And so then to make kind of clean distinction, the underlying science, underlying method we refer to as the low pressure pulse technique. And then what we've developed as a company to commercialize is Pulse as a product. So here on the screen, you can see an image of where we are today. So rather than the piston method that was originally developed, and obviously all the testing that was done on a garage compressor type configuration, we've now streamlined all of that switchgear into what you see on the screen, which is a nice portable, professional-looking unit, compressed air-based portable compressor used to pump up the air receiver, that canister in the middle, and then the controller on the bottom left there, used to control and execute the test itself. And that controller is what's used to record the background pressure in the room as well. So naturally, there was, as you heard from Chris, a lot of work that's gone on in the field of academia, PhDs, and lots of fundamental research and development that have gone into Pulse. But when we inherited it and sought to commercialize it, our first task was to try and get acceptance under the regulations of the method. So in partnership with the University of Nottingham, we went away and did some further field trial work, as well as bringing in some other kind of third-party professionals to review the method and the data. So again, this is just a snapshot really, but I think back in 2018, we did quite a large field trial of 119 homes with blower door pressure and depressure versus kind of pulse testing. In all of those 119, we did 3 repeat pulse tests. So across that whole data set, we saw very strong repeatability of pulse. And as you can see on the chart on the right, there's clearly a linear relationship. The two methods aren't fundamentally measuring anything wildly different from one another, which is encouraging. We've also got a data set of 24 homes where we've got pulse alongside blower door, but then also tracer gas and decay test results. So that's been the subject of PhD work, and naturally trying to look into this relationship between higher pressure 40-50 Pascal tests, lower pressure pulse tests 4 Pascals, and infiltration at under natural conditions. We've also commissioned the BRE, so they undertook what's termed environmental technology verification. So there's a nice international standard around that that helped further with our verification of our performance claims of the product. And the National Physics Laboratory also did a third-party review, which all culminated, like I say, to help us get regulatory acceptance of the method in the UK. So just in terms of like the marketing messages we have around this then, and Chris has talked in quite detailed technical terms, essentially the essence of the product is compressed air-based means of rapidly measuring air leakage directly at low pressure. And so the key USP therefore is that you're measuring the air leakage rates representative of much normal kind of occupied conditions. Very simple user operation. So you place the cylinder centrally on the ground floor, all internal doors open, input the building volume and press go, and the test does the rest. So you're not concerned about position of pressure tappings, mounting of any equipment in the envelope itself, whether it's a doorway or a window. It's all quite a neat self-contained piece of kit. Very low disruption, so it's that instantaneous quick burst of air, and you get an immediate readout of the result on the screen. So it's not particularly disruptive or onerous on an occupied home. And then, as we've kind of stressed throughout these slides, extensive validation has taken place, and as of today, the method is approved under a range of UK policy initiatives, but including the main UK building regulations. And the method is documented in this CIBSE TM23, which is the approved procedure that's available today from the CIBSE website. Mindful of time, so many of you might scoff at the kind of, it's not an enormous data set by any means, but I think what's quite exciting is that we're starting to now build up a data set for the first time of how buildings behave and perform air leakage wise directly at 4 pascals. So we've got 20,000 tests and counting. A large proportion of these tests are carried out in existing UK homes, and you can see here we've got quite an interesting distribution curve. Actually, quite a lot of existing homes, probably more airtight than what we would have otherwise previously thought. And so, yeah, naturally this data set's growing, and I think will be really interesting as time goes on to kind of, yeah, it's a new kind of area of understanding of buildings, I think. Final slide then. So in our view, airtightness testing needn't be one size fits all, a single product market. This isn't about developing new techniques to displace the incumbent blower door by any means. It's about trying to open up new frontiers, new opportunities. As you've heard today, we've done a lot of work in terms of development and validation over quite frankly, decades. So we're strong of the view that UK regulations have set a precedent with the TM23 document. And so there we have a globally accessible third-party standard. I know we're talking to the ISO committee around 9972 and whether there can be revisions to that, but clearly that takes time. And so there's a global market for pulse across numerous fields, whether that's very conventional kind of traditional testing of new and existing homes or non-residential buildings, or perhaps even testing things like containment labs, refrigeration chambers, things where maybe a blower door fan is more difficult to mount. And yeah, it's a different tool. It's another tool in the toolbox. So it presents numerous new opportunities. And yeah, all of this evidence that we've shown you kind of very briefly in these slides today is available on our website. And as Chris has said, kind of there's lots of peer review papers out there as well. I think at that point we'll open up to some questions, I believe. Thank you.